Okay, ladies and gentlemen, welcome back to Vector Calculus. Welcome back. Now, we've already spent a couple of introductory lectures on Vector Calculus. In particular, in the two previous lectures, we defined vector fields and calculated flow lines. We also talked about the divergence of a vector field. And divergence is a simple operation that can be thought of as a type of derivative from vector calculus. Now, in today's lecture, we're going to look at another operation known as the curl of a vector field. Now, these two concepts here, they complement each other. Okay? Now, the divergence, when applied to a vector field, produces a scalar field. The curl, on the other hand, we'll see that when we apply the curl to a vector field, it will produce another vector field. Okay. So, what is the curl? How do we define it? Well, as I said before, the curl can be thought of as another type of derivative from vector calculus. And we can define the curl in terms of a cross product between the del operator and a given vector field, f. Okay? Now this del, remember, is just a symbolic vector that can operate on given vector fields. Gentlemen, push. Okay, so in this particular definition of curl, you'll see that the del operator and the given vector field, they're tied together by this cross product. Okay? So in this bottom line here, I guess the formula or the expression for curl is written out explicitly. Now, I wouldn't recommend that you memorize this because it's quite complicated. What I like to do is actually write everything out as this type of determinant and then just expand the determinant along the top row. Okay, so that's the curl of a vector field. Where does it come from? And how do we calculate this to a few examples? Well, let's do an example first and just calculate the curl of a given vector field. Okay, so by definition, the curl of a vector field is just the del operator crossed with the given vector field, right? So here, it can be written in the following way. Okay, so I expand that determinant along the top row. Okay, and to do that, a good way that I like to go here is go, all right, well, I is in the first column and the first row. So I cover the row and column that I appear in, and then I multiply I by the determinant of what's remaining. Then I move on to J. J is in the first row and the second column. So what I do is I multiply j by the determinant of what's left, not forgetting the minus sign in front of the j. And then I move on to k. K is in the first row and the third column. I multiply k by the determinant of what's left. So that's basically what I'm going to do. Okay. Okay, so that's the first part. Don't forget the minus sign here. A lot of people forget the minus sign when they expand these determinants. Okay, so now we've reduced it down to the evaluation of 2 by 2 determinants. Now, remember here, when we expand these, we're not really multiplying, we're operating on the given functions. Okay, so let's expand that out. The first determinant is going to give us d dy of x squared y to the fourth minus d dz of z cubed. Okay, so it's going to be something like 4x squared y cubed minus 3z squared times I. All right, move on to the second one. Again, go diagonally. It's d dx of x squared y to the fourth minus d dz of x squared. So that term is going to be 0. This term is going to be something like 2x y to the fourth. Now, in the last determinant, you can see if we expand that diagonally, right, d dx of z squared 0, d dy of x squared is 0. So it's not going to add anything to our answer here. All right, so here's our answer. It's in a vector, right? And notice a couple of things. If I go back to the original problem, you'll see we have i's, j's, and k's present here. But in our answer, we only have, well, i's and j's. Right? This is trivial. All right. So here's another example. Given the following vector field, calculate the curl of this vector field. Now again, the k component here is 0. So let's go through and calculate the curl and see what this produces. Okay, so again, just expand along the top row and break it down to the evaluation of 2 by 2 determinants. d dy. Don't forget the minus here with the j. Oops. y squared. Okay, so have a look now at the determinants here. If we expand this one, we're going to get 0. If we expand this one, we're also going to get 0. However, if we expand this one, we're going to get some terms here. So okay, so what are we going to get? We're going to get 3x squared plus 2y. Okay. Okay, so why is that example interesting? Well, let's go back to the question. The given vector field has a 0k component. In fact, this vector field, you can think of it as just lying in the xy plane, right? But when we apply the curl to that vector field, we get a new vector field that will have a non-zero k component for certain x and y, right? So at school, or possibly in first year university, you learn that the cross product of two vectors produces a normal vector to the plane that those two vectors lie in, right? The curl will produce a similar vector. Thank you. Okay. So, you can think of the curl as producing some type of normal vector. Okay. All right. All right. So we've learnt how to calculate the curl. It's very mechanical. Essentially, it's just got to do with expanding a determinant. Now, what does the curl actually mean? Well, very loosely speaking, the value of the curl at some point P is a measure of which the given vector field swirls around the point P. Now, I'll make that more precise in a little while. Okay? Now, just very simply speaking, we can use what's called paddle wheel analysis to look at the curl of a given vector field. Okay? So, suppose we're working in the plane, in the xy plane, and this is a vector field, and suppose it represents the velocity field of a fluid. What you do is you place a paddle wheel centre at P with its axis perpendicular to the plane and observe if and how the paddle wheel rotates. Is there rotation, and in what direction? Is it clockwise rotation, counterclockwise rotation? And then we can make some conclusions about the curl of our vector field. So this is without doing any calculations whatsoever. So how are these things related? Well, a non-zero curl means that the little paddle wheel would rotate. Now, in 3 dimensions, the idea of curl is similar. It's about rotations and swirling around points, but it's much harder to visualize. Okay? So we're just going to stay in the xy plane at this stage. Okay, so to make things a little bit more precise, if we're in the plane, and the curl of the vector field at a given point P, dotted with the k vector, is positive, then we have counterclockwise rotation about the vertical axis. All right? And if this dot product here is negative, then we have clockwise rotation, and we can predict what our little paddle wheel, we can observe what our paddle wheel does, and then make a statement about the curl. All right, so how does this work in practice? Here's a good example. Imagine just for a second you don't have the vector field here, the equation for the vector field. You're just given the field plot. And the question asks you to calculate or make some observation about the curl at the origin, for example. Okay? Now, this is called the scalar curl. So it is the k component, right, of curl of f. Right, so it's a function, a real valued function. So, for example, this here, that's called the scalar curl. Okay? All right. Okay, so let's put our little paddle wheel in. See if it rotates. Well, you can see from the field plot that we're going to get rotation, yes? And it's going to be in a anti-clockwise direction. So our paddle wheel rotates in an anti-clockwise direction. Well, what does that mean? It means that we can say that our scalar curl is going to be positive. At the origin. Well, I know you can see this here and go, well, I can just calculate the curl directly from that. But imagine you're not given the vector field. You're just given the picture. Okay, here's another one. So again, imagine you're given the vector field, the picture of the vector field, but not the precise representation. We can see that if I again draw a little paddle wheel in, centered at the origin, am I going to get rotation? Yes, we are. In a clockwise. Direction. Thus, the curl of our vector field is negative, say at the origin. Okay. Now, you need to be careful. Some vector fields, on the surface, they don't look like there's any rotation going on. And here's a good example. It doesn't look like there's any rotation going on there. But, again, if I draw my little paddle wheel in and say center it at the origin, is there going to be rotation? Well, yes. Our paddle wheel will rotate in a clockwise direction. Thus, the scalar curl of f at the origin will be negative. And again, you can just go through and calculate the scalar curl from the given. Yes?
But given outside the x-axis, there's a rotation.
Yeah, I'm just keeping it very simple. I'm just looking at yeah, if you moved away, for example, to another point, right? So let's go up here. Is there rotation going? There. Yes, you're right. Okay. The nice thing about these examples is the scalar curl is constant everywhere. So it'll have the same properties no matter where you are in the plane. Okay? Okay. All right, so here's another one. Again, I'm just going to concentrate on the origin here. Will our paddle wheel rotate? What do you reckon? No. No rotation. Okay, so we can conclude that the scalar curl is 0. And again, another simple example. This is the radial field that we saw in our first lecture on vector fields. Any rotation going on? No. Okay, so there's some good geometric ways of making some conclusions about the curl of a given vector field, but only, I guess these ones are just done in the xy plane, so things are nice and simple. Now, if the curl of a vector field is the 0 vector, then we call such a field irrotational, because there's no tendency to rotate or swirl around points. Okay, so here's an example. Consider the following vector field plot. I've just done the following vector field plot with field plot in Maple. And we're asked to calculate whether the scalar curl is positive, negative, or 0 at the origin. So let me just pop this in. Okay, so what's it going to be? Positive, negative, or 0? 0, right. Again, you can draw in your little paddle wheel. There's no rotation. No rotation there. So our paddle wheel does not rotate. And so the scalar curl is 0. All right, some basic identities involving the curl. Like I said at the start of the lecture, you can think of the curl as a type of derivative from vector calculus. Question?
Is the curl only defined to vector fields up to 3 dimensions?
Yes. Yes. Divergent, okay, so the curl is only defined on vector fields up to 3 dimensions, but something like divergence, you can define that on n dimensions if you like. Okay? So what basic identities are there for this curl? What basic identities are there? Well, the first one can be thought of as additivity. Okay, the second one, the divergence of the curl of f. So div curl f. How can we interpret that? Well, it means that curls are incompressible. Okay? Remember, we call a vector field incompressible if the divergence is 0. So think about the vector field curl f. Right? So curls are incompressible. Next one. Curl grad phi equals the 0 vector. What does that mean? Well, it means that gradient fields are irrotational. Okay? Use your gradient field here. Gradient fields are irrotational. And the final identity, well, that's like a product rule for the curl. So each of these identities have a role to play. They're very handy when you're trying to simplify complicated expressions. If I have enough time, I'll come back and prove some of those a little later. Okay, so now let's talk about the so-called circulation density and the curl. If you remember back to a previous lecture, we talked about divergence and flux density, right? Now, when we talked about divergence, we looked at the same rectangle as this one, and we looked at the flow rate over each side, and then divided by the area, and shrunk the rectangle down to a point. Now, with the curl, it's similar, but what we're going to do is look at the flow rates along each side. Okay, so we're not going to look at the flow rate across each side, or normal to each side. We're going to look at the flow rates along each side. Okay? Okay, so here I'm going to draw in some unit vectors at certain points. Okay, so how do I calculate the flow rates along each side? Well, again, I'm just working in the plane here. So I'm going to just represent the components of my vector field by two functions, m and n. And essentially what I'm going to do is, to work out the circulation around the rectangle, I'm going to approximate the flow rates along each side and add everything up. So, how do I calculate the flow rate along, say, this bottom edge? Well, I'm at the point x, this corner, xy. The flow rate in this counterclockwise direction will be the component of f at that point that lies in the direction of I, or the component of f at that point along I. So it's just a dot product, times the distance, of course. Okay? So along the bottom edge, the flow rate is the following, right? It's F, the vector field F, evaluated at that point, and we look at the component of F in the direction of I, multiplied by delta x. So it's just a dot product. Okay, so now I can just go up to here and simplify that. I guess I should have approximately equal to here. So it's going to be m x y delta x. Okay, what about the flow rate along this right side? Well, we're at the point x plus delta xy, so it's going to be f evaluated at that point, and we look at the dot product between f at this point and j. So that is the component of f that lies along j at that point. So the flow rate is approximately equal to F at the point in question dotted with J times the length of the side. So that's just going to be something like n of x plus delta x, y times delta y. Okay, so let's think about the flow along the top edge now. Notice I'm going to approximate that at this point. So it's going to be f evaluated at that point dotted with minus I times the distance. So the flow rate is approximately equal to, what's it going to be? In this case, it's going to be minus m x y plus delta y times delta x. All right, and for the left edge, or the left side, you can see I'm at the point here. I'm going to dot f at the xy with minus j and multiply by the distance, delta y. So along the left edge, the flow rate is approximately equal to, what's it going to be? It's going to be something like minus n xy delta y. So, to work out the circulation around the rectangle, we add up all the flow rates. So the sum of the flow rates well, I guess it is equal to it, isn't it? Okay, we get 4 terms. Now, we do something now to produce some partial, well, I guess it'd take approximations to partial derivatives, just like we did with the divergence. Okay, in the first 2 terms, I'm going to divide and multiply by delta y, and in the second 2 terms, I'm going to divide and multiply by delta x. So you can see that the top term is going to be approximately equal to this derivative. These 2 terms here are going to be approximately equal to dn dx times delta x delta y. Now we can factorise off the delta x delta y. That gives us the area for the rectangle. So what we do is we divide the circulation around the rectangle by the area of the rectangle. Now if we let delta x and delta y go to 0, then we obtain the so-called circulation density. So basically the rectangle shrinks down to a point. So the sum of the flow rates divided by the area of the rectangle is approximately equal to dm dy plus dn dx. Okay, so if we let delta x and delta y go to 0, then we shrink our rectangle down and we obtain the so-called circulation density of F at the point x, y. Now, does this look familiar? Well, it's just the scalar curl, right? It's just the scalar curl. So let delta x and delta y go to 0 to obtain the circulation density of F at the point x, y. And you can see that it's just equal to the scalar curl. Okay, so there's not much difference between this type of analysis and the analysis we did with divergence and the flux density. Okay, the only difference is that we draw the same rectangle, and instead of looking at flow around the rectangle, we're looking at, in this case, while with the divergence, we're looking at the flow across the boundary of the rectangle, right? Across the sides. So here's our rectangle again. Here we're looking at the flow along the sides. With the divergence, we were looking at the flow across the sides, right? Okay, so here are some basic identities from vector calculus. Now there's a lot there, but what I try to do is I try to remember them in simple ways. Okay, that's why I've given you those phrases. especially with the three identities that we looked at today. Now, you can prove all of them if you want to. I'm going to prove a couple because we've got a little bit of time. So, I guess the most simple way to prove these things is in a component-wise fashion. Sometimes you can use Einstein index notation and summation notation. That's very fast if you can master the notation. So let's have a look at some basic identities involving curl. Okay. Well, let's prove that curls are incompressible. Okay? So I'm going to give this a label, star, and we'll prove that star holds. All right, so let our vector field have the following components. Now, F1, F2, and F3 are all functions, and it turns out that for the proof here, we're going to need Clairaut's theorem, right? Clairaut. The mixed derivatives theorem, right? A famous French mathematician, Clairaut. Do you know him? Have you heard of him? No? No? Okay, well you have now. All right? All right, so now the curl of F. Now I'm just working off the second slide that I presented today, where we define the curl. You could go through and work out using the determinant and all that stuff, but I'm just going to write it straight out of there. All right, so here's our curl. And what we want to do is take the divergence of this curl. Okay, when we take the divergence, we're going to get a lot of mixed partial derivatives. And then hopefully, they're going to cancel out. So the divergence of our curl. Well, what we do remember is we look at the first component and take the partial derivative with respect to x. We look at the second component and take the partial derivative with respect to y. Then we take the third component and take the partial derivative with respect to z and add them all together. Okay, so up here we're going to get d squared f3 dx dy minus d squared f2 dx dz. Now we're going to get d squared f1 dy dz minus d squared f3 dy dx. And we're also going to get d squared f2 dz dx minus d squared f1 dz dy. So we've got 6 terms there, and we want them to cancel out. Can anyone tell me what conditions do we need to assume to make all those terms disappear? Yes? Yes, continuity. Continuity, yes. Continuity of what? What do you mean when you say partial derivatives? There's lots of different kinds. You're on the right track, though, Ian? Yeah, who said that? Good. Why? Why did you say that? That's right. Yeah. Well, let's just assume. Let's just assume what. Like, let's just make the minimum assumptions. I mean, you're right, Ian. If F1, F2, F3 have all continuous partial derivatives of all orders and all types, yes, you'll get it. But so this one will cancel out. Hang on, have I missed one? What have I missed? Oh no, this one will cancel out with this, right? This one will cancel out with this. This one will cancel out with this, right? Assuming the mixed derivatives are continuous everywhere, let's say. Right? So the theorem here is Clairaut's theorem. Okay, if you try to, for example, prove that gradient fields are irrotational, then to get the proof to work, you'll need to make assumptions on the phi here, the scalar field phi. And the assumptions about the mixed partials are similar to the previous example. So, that's the curl. We know how to compute it. We have some physical idea of where it comes from through circulation density. Any other questions on the curl of a vector field? Yes, Ian.
You said that when we prove these,
Yep.
we have to make some assumptions on the
Yes.
vector field. Does that mean that for some vector field, this might not stand?
Correct. Yes. I mean, we're essentially what we're doing here, we're assuming that, as you said before, the vector fields are all nice and smooth. Right? So yeah, it won't hold necessarily for all vector fields. Okay. Right? I haven't mentioned that in the slide because we'll be dealing with nice, well-behaved vector fields with nice, smooth components. Okay? Any other questions? Okay, I'll see you all this afternoon.